This video contains the solutions for the Unit 2 Applied Mathematics AS level qualification for WJEC, and this is the sample assessment materials. This particular paper has 41 marks for statistics and 34 marks for mechanics, so overall it is a 75 mark paper. You have 1 hour and 45 minutes to answer this paper, which is 105 minutes. So if we divide 105 by 75, it means you have 1.4, which is 1 minute 24 seconds roughly per mark. You'll be given a question paper along with your answer book, a formula booklet and the statistical tables. You need to bring your own calculator. Section A, Statistics. The first question is probability. We're told that events A and B are such that the probability of event A occurring is 0.2 and the probability of event B occurring is 0.3. We want to determine the value of the probability of A or B in 3 different cases. So I would always recommend writing down the probability of A equals 0.2 and the probability of B equals 0.3 on your answer sheet. So first scenario is when the events are mutually exclusive. Mutually exclusive events cannot occur at the same time. So if we were to illustrate them on a Venn diagram, there would be no overlap at all between the 2 events. Because of this fact, the probability of A or B is the same as the probability of A plus the probability of B. So in this particular case, the probability of A is 0.2, the probability of B is 0.3, and 0.2 plus 0.3 equals 0.5. The second case is when A and B are independent for part B. Two events are independent when this is true. The probability of A and B occurring is the same as the probability of A multiplied by the probability of B. So whenever you see the word independent, you have to use this rule at some point in your answer. We are looking to find the probability of A or B. Now we know from our formula booklet, in general, the addition law for multiplication is that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That's because these events are no longer mutually exclusive, so if we were to draw a Venn diagram for them, there would be an overlap in the middle, which is why we're subtracting A and B, because it would occur twice otherwise. This formula is given to you in the formula booklet. So we're looking to find A or B. We know A is 0.2, we know B is 0.3. We don't know A and B, but we do know, because they're independent, that A and B is the same as A times B. So we can say subtract the probability of A times the probability of B. So we've got 0.2 plus 0.3, subtract 0.2 times 0.3. 0.2 plus 0.3 is 0.5. 0.2 times 0.3 is 0.06. So 0.5 subtract 0.06, which gives us 0.44. The last scenario is this scenario here. So we've got A, and then this shape here, and then B. Well, this here, this means subset of. So what this means is that A is a subset of B. That means that everything in A is also in B, but B has other stuff as well. If we were to illustrate this on a Venn diagram, we would show that A is fully inside of B. That's because everything that occurs in set A is also in set B. Because of this, when we want to calculate the probability of A or B, it's simply just the probability of B. Because A is fully within B, then if we want A or B, we just need B, because that includes A anyway. And the probability of B is 0.3. Question 2 is hypothesis testing. Part A is asking us to state hypotheses to be used to resolve the difference of opinion. We have to look back at the question to get our hypotheses. So first of all, we're looking for the probability we think is correct initially. So we're told that Derry believes his support is 45%. So our null hypothesis, denoted by H0, is that P equals 0.45. The null hypothesis is always equals. The alternative hypothesis will be based on the language in the question. So we're either looking for a less than, greater than, or not equal to. This question says, his agent, however, believes that the support for him is less than this. So it's quite clear that the alternative should be P is less than 0.45. The next part of the question tells us the critical region. The critical region is X is less than or equal to 20. Remember, the critical region is the region that if you fall within that region, you're going to reject the null hypothesis. So if 20 or less voters say that they support him, then we're going to reject the 45% and we're going to accept that it's actually less than 45% support for him. We want to find the significance level of this critical region. So looking at the question there, we're dealing with 60 electors. So we're dealing with a distribution that is binomial with an n of 60, and our p is taken from our null hypothesis. Our p is 0.45. So we're looking for the probability. That's the probability x is less than or equal to 20 using this distribution. So on your calculators, you need to be going to menu 7 for distributions, and we scroll down to binomial cumulative, which is number 1. We want just one outcome, so we're just looking for a variable because we're only finding one probability. Our x is this value here is 20, our n is this value here is 60, and our p is this value here, which is 0.45. That gives us a probability of 0.0446. In other words, a 4.46% significant level. So we have now done question 2A and question 2B, part I. Now, B part II or B part 2, it doesn't make sense to come before B part 3 in my opinion. So I'm going to do part 3 next, which is explain in context the meaning of a type 2 error. A type 2 error is always accepting the null when it's actually false. So in this case, a type 2 error would be accepting that Derry support is 45% when it is actually false, or when it is actually when we're giving the question what value it could be, it's actually 0.35. So it's actually 35%. Now that's what a type 2 error is. It's accepting that Derry support is 45% when it's actually not 45%. So it's accepting the null hypothesis when it's actually false. So to find the probability of that, so now going back to part 2, the probability of a type 2 error is to find the probability of the acceptance region, where if the critical region is x is less than or equal to 20, the acceptance region is greater than or equal to 21. You want to find this probability, but with the new probability. Instead of 45%, we're going to be using 35%. So our distribution is now binomial with an n of 60 and a p of 0.35, not 0.45. Now our calculators or tables couldn't look up a greater than or equal to, so we have to do 1 minus the probability x is less than or equal to 20. So on your calculators, our x is 20, our n is still 60, but our p is 0.35 now, not 0.45. So it's 1 minus this. So it's 1 minus 0.4516. And to do this easily without retyping this into your calculator, press menu 1, which is the calculator mode, and then just press 1 minus answer equals, and we get 0.5484. And that's how we find the probability of a type 2 error. Now, the final part now is explain briefly why this test is unsatisfactory, how could it be improved. Well, it's unsatisfactory because the probability of error is too high. It's unsatisfactory because the probability of error is too high. The probability of error, or type 2 error specifically, is 55% because it's 0.5484, which is too high. And the way to improve this is to take a larger sample. So the error could be reduced by taking a larger sample. Question 3 is a Poisson distribution question. It's telling us cars arrive at random at a toll bridge at a mean rate of 15 per hour. Explain briefly why the Poisson distribution could be used to model the number of cars arriving in a particular time interval. Easiest thing to do is show you the mark scheme for this one. The Poisson distribution can be used when arrivals can be assumed to be independent, where we're told they're arriving at random, and at a constant mean rate. So we're going straight to part B. So part B, Phil stands at the bridge for 20 minutes. Well, we knew that the mean was 15 per hour. So if Phil is standing at the bridge for 20 minutes, that's a third of an hour. So our distribution is Poisson. Instead of a mean of 15, we divide it by 3, which is a mean of 5, because he's only there for 20 minutes. Determine the probability he sees exactly 6 cars arrive. So it's the probability x equals 6. Now you can use your calculator for this, but let's practice using the formula. So the formula in general is e to the minus lambda, where lambda is the mean, times lambda to the power x, where x is the probability you're trying to find, divided by x factorial, and this formula is given to you in the formula booklet. So in this case, the formula is e to the minus 5, because 5 is our mean, times by 5 to the power 6, because 6 is the number we're looking for, divided by 6 factorial. And the answer for this is 0.1462. So if we wanted to practice using our calculator for this, you would need to press menu 7 to get distributions, and you want Poisson PD, because we're finding exactly an exact probability, not a cumulative, not more than 1. So number 2, and we're just finding one of them. We don't need lots of answers, so we use variable. Our x is 6, and our mean, our lambda, is 5. And there we are, our probability of 0.1462. Part C of question 3 is to use the statistical tables provided to find the time interval in minutes for which the probability of more than 10 cars arriving is approximately 0.3. Well, the probability x is greater than 10, more than 10, we can't find in our tables because they show less than or equal to probabilities. So greater than 10 is the same as 1 minus the probability x is less than or equal to 10. Because greater than 10 means 11, etc. upwards, and so that's 1 minus 10 downwards. So we're looking for the probability that x is less than or equal to 10 being close to 1 minus 0.3. So in our Poisson tables, we are looking across the rows at 10, because this is showing less than or equal to 10, and we're looking for the probability that is 1 minus 0.3, so the one that is closest to 0.7. And we can see here, this one here is the closest one to 0.7. 1 minus this would be 1 minus 0.7060, which is 0.294. That's the closest to 0.3 we're going to get, and that is for a mean of 9. So we know that lambda, the mean, equals 9, because we were looking for the probability of more than 10 cars arriving to be equal to 0.3. We can't look that up in our table, so we look up 1 minus that. So we were looking up 1 minus 0.3, which was 0.7, and the mean of 9 gave us the closest answer. So if the lambda's 9, remember we knew that cars arrived at a mean rate of 15 per hour, and we're looking for the number of minutes that he stood there if his mean was 9. So let's look at 9 as a fraction of 15. So 9 divided by 15 is 3/5. So that simplifies to 3/5. So what is 3/5 of an hour? Well, it is 3/5 times 60, which is 36 minutes. Okay, question 4 is quite lengthy and it does incorporate some of the data topics. First of all is sampling. So there's lots of information we need, but the first paragraph is most relevant here. So a researcher wishes to investigate the relationship between the amount of carbohydrate and the number of calories in different fruits. He compiles a list of 90 different fruits. He wants to select a simple random sample of 14 different fruits from the list. Explain how the random number function on a calculator could be used to select this sample of 14 different fruits. Well, we first have to start by saying he needs to number the fruits 1 to 90, and we're using 2 digits. He then needs to use the random number generator on his calculator. So use the random number generator to generate a random number between 1 and 90. Because then, once he has his random number, he is going to select the fruit from the list that's already numbered. That has the corresponding number. So that gives him one fruit sample from the list. We want to repeat this process until we have 14 different, that's important, fruits. In other words, we're going to ignore repeats because we want a simple random sample. Now this question only asked us to describe the sampling technique, but just in case there was a question where you actually had to do this, let's just remind you of how to use the random number generator on your calculator. So the random number generator is located here. The decimal point is the pink function. So it's alpha to get the pink function decimal points, gives you random number integers. We want from 1 to 90, so we press 0, 1, and then you need the comma, which is shift close bracket, 90, and then close the brackets. Every time you press equals now, our calculator will generate a random number between 1 and 90. It will sometimes throw up repeats. That's why we need that statement in our explanation that we're going to ignore repeats if we want a simple random sample. Now that he's sampled his 14 samples, we're actually going to look at how the data can be analysed. So we have a scatter graph already drawn for us, and the first question about the scatter graph is asking us to describe the correlation between number of calories and carbohydrate. Now you want to be using strong negative or no correlation, positive negative or no correlation, but also the words strong or weak. So in this case we're going uphill, so it's a positive correlation. It's quite close to a straight line, so we can say it's a strong positive correlation. So B part I, strong positive correlation. The next part basically asks us to interpret that in context. So in other words, the more carbohydrates there are in a fruit, then the higher the number of the calories. So we can say more carbohydrates in a fruit suggests more calories. But you literally just have to mention the two x and y variables in context. Now the next part of the question is regression lines. Now remember, back in GCSE we would draw a line of best fit by eye through these points here. Now this regression line is basically the equation of the perfect line of best fit through these points. So the equation of this line of best fit, the regression line, is the number of calories equals 12.4 plus 2.9 times carbohydrate. So that carbohydrate is your x variable and the number of calories is your y variable. So it's basically the form y equals mx plus c. So we're asked to interpret the gradient of the regression line. So the gradient is the coefficient of the x variable. So in this case it's 2.9. And to interpret the gradient, it's always the same idea. You always consider for every 1 unit increase in x, then that coefficient, that number in front of x, is the increase or decrease in y. So in this case, in context, for every 1 extra carbohydrate, so every 1 extra gram of carbohydrates, so for every 1 extra gram of carbohydrates, so that's the increase in x. That number there, 2.9, tells us the increase in y. So for every 1 extra gram of carbohydrates, there is a calorie increase, our y variable, of 2.9, and the unit is calories, so cal. The last part of this question is to explain why it's reasonable for the regression line to have a non-zero intercept in this context. In other words, it crosses the y-axis not at 0. Well, let's have a think about this in context. If we had 0 carbohydrates, does it mean 0 calories? Well, not necessarily, because just because there's no carbohydrates, there may still be calories, for instance, maybe from fat. So all you want to say is, if x equals 0, or in context, if there is no carbohydrates, there may still be calories present, e.g. from fat. Okay, question 5 is another question that incorporates lots of data work. So we're talking about Gareth and his interest in pop music. The main statement is, he read a claim in a magazine, in the pop industry, most songs on the radio are not longer than 3 minutes. He investigates the claim by recording the length of the top 50 singles in the UK official singles chart for the week beginning 17th of June. Comment on the suitability of this sample to investigate the magazine's claim. Easiest thing to do is show you the mark scheme here. The mark scheme says, we cannot be sure that the sample is representative without knowing how the UK official singles chart is constructed. It could be that it's just certain types of pop songs, not all type of pop. It could be that they actually cut down the track lengths and they aren't actually representative of their true track length. But the main thing you're looking for is to say that the sample, we can't be sure the sample is representative by giving a valid reason for that. But that's the key phrase you're looking for, is that we can't be sure the sample is representative because we don't have enough information. Then Gareth records his data in a table, and then he produces a histogram. We're asked to state 2 corrections that Gareth needs to make to the histograms that actually represents the data in the table. Well, one of the purposes of a histogram is to represent continuous data, which length of time is. But the only problem is they've got gaps between the bars. Now we can't have gaps between the bars on a histogram because histograms represent continuous data, so we can't have gaps. So that's the first correction. The second one is, looking at the table, we've got 2.5 to 3, which is here fine. Then we've got 3 to 3.5, and then 3.5 to 4. Well, our histogram goes from 3 to 4. It should go 3 to 3.5 with a height of a frequency area of 17, and then it should have a width of 3.5 to 4. Gareth has then produced a box plot for the lengths of the singles. Here's his box plot here. So remember, this line's the median. Then you've got your lower quartile and upper quartile making your interquartile range. Then you've got your lowest value and your highest value, except this star or cross means an outlier. So he sees there is one obvious outlier. What will happen to the mean if the outlier is removed? Well, the mean is when you add up all the data and divide by how much data you've got. So we're adding in this extreme value. So if we took out the extreme value, the mean would decrease. Part 2. What would happen to the standard deviation if the outlier is removed? Remember, the standard deviation is the spread of the data away from the mean. Well, if the mean is going to decrease and you haven't got this extreme value that's far away from the mean, then your standard deviation will also decrease. So Gareth decides to remove that outlier. He then produced a table of summary statistics. So here is his table of summary statistics. Use the appropriate statistics from the table to show by calculation the maximum value for the length of a single is not an outlier. Remember, the calculation for an outlier is always either the lower quartile, take away 1.5 times the interquartile range, or the upper quartile, Q3, plus 1.5 times the interquartile range. If we have a value below this or above this, then they are outliers. We're ignoring this one for now because we're testing at the maximum at the upper end, so we're using this here. So first of all, we need the interquartile range. The interquartile range is the upper quartile minus the lower quartile. So 3.89 minus 3.26. We then want to times that by 1.5, and that will give us 1.5 times the interquartile range. So doing that calculation, 3.89 minus 3.26, that's our interquartile range, and that is 0.63. We're timesing that interquartile range by 1.5, which gives us 0.945. So if we add that to the upper quartile, which is 3.89, then that will give us the upper boundary for an outlier. So 0.945 plus 3.89 is 4.835. So anything above 4.835 is an outlier. However, our maximum was 4.38. So 4.38 is below the boundary for an outlier, so it's not an outlier. The next part of the question is to state with reason whether these statistics support the magazine's claim. I remember the magazine's claim was that in the pop industry, most songs on the radio are not longer than 3 minutes. That was the claim. Well, looking at this table of summary statistics, the median is 3.6. Now remember, the median is half the data halfway through. It's also a measure of average. In other words, the average length of single is actually 3.6 minutes, which is obviously bigger than 3. Also, we know that at least half of the singles are longer than 3.6. Therefore, the magazine's claim is false or not supported. For the last part of this question, we're now having to look at Gareth's own personal collection of singles, and he's done the similar summary statistics for his. We're comparing his summary statistics to the summary statistics of the UK singles chart. We have to compare and contrast, and we have 3 marks to do this. So you need to be giving 3 points for those 3 marks. So when you're comparing, always comment on the median, because that's a measure of average. So Gareth's median is 2.92 minutes, whereas the UK singles chart is 3.6 minutes. So on average, Gareth's singles are shorter. The other thing you want to be mentioning is the variation. So the variation is given by the interquartile range and the standard deviation. You can use either or the overall range. Now we're given the standard deviation for both, so that is the spread of the data away from the mean. So you can see the singles chart is 0.393, Gareth's is 0.364. So we're comparing standard deviation, and Gareth's is lower, which means that there's less variation in his singles or that they're more consistent. So Gareth's singles are more consistent in length, or we can say there is less variation. And that's because of a lower standard deviation. Now the last point is to look at the skew. Now the singles chart has a roughly symmetrical skew. In other words, the median and the upper quartile, the lower quartile, they're all roughly symmetrical. However, Gareth's singles, more than half of them are shorter than the mean length. The mean is here 3.13. More than half of them are shorter than this because the median is 2.92. So that means that Gareth's would have a positive skew. Whereas the singles chart has roughly a symmetrical skew. So that's another comparison you can make here. So now we come to section B, the mechanics section. So starting with question 6, we have a small object being dropped from rest from the top of a building. So this is a vertical motion SUVAT question. So I'd like to do a little sketch to start with. So we're told the building is 160 metres high, just so we can get an idea of what's happening. and the object is being dropped from rest. We want to calculate the speed of the object as it hits the ground. So we're dropping it, so down is my initial direction, so therefore down is my positive direction. So I set up SUVAT, S-U-V-A-T. Remember, S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time in seconds. So our S is 160 because the building is 160 meters high, so the object's being displaced by 160 meters. U is our initial velocity, which is 0 because it starts at rest. V is our final velocity, which is the speed it hits the ground with, which is what we're looking for. And A is acceleration, which is gravity, and because our initial direction is downwards, which is positive, then gravity is positive 9.8. We're not dealing with time in this part here. So we need an equation that involves S, U, V, A, and T. So we need V squared equals U squared plus 2AS. So now substituting in the values, we've got V squared equals 0 squared plus 2 times 9.8 times 160. So V squared equals 3,136. So V is the square root of 3,136. So V is 56 meters per second. That's part A. Part B, determine the time taken for the object to reach the ground. So we have the same situation. We have the object being displaced 160 meters, an initial velocity of 0. We now know V is 56. We have gravity of positive 9.8, and we're looking for time. So actually we can use any of our equations because we're finding T and we know everything else. However, I would tend to ignore the answer that you've discovered yourself. So I'm going to ignore V equals 56 because I discovered that myself. It's more reliable to use what I was given in the question. So I'm ignoring V. I'm using the formula S equals UT plus a half AT squared. So 160 equals 0 times T plus half times 9.8 times T squared. So in other words, 160 equals 4.9 T squared. So if I divide 160 by 4.9, I'll get T squared. So T is going to be the square root of 160 divided by 4.9, which works out to be 40/7 seconds. If you've rounded this to a decimal, you should have 5.71 seconds. Now part C, state one assumption. Well, let's state them all, just so you know what our assumptions are. When we're using SUVAT, we are assuming that the object is being modelled as a particle. We are also ignoring any other forces apart from gravity. So we are ignoring air resistance, other external forces other than gravity. Question 7 is a pulleys question. Now, although the pulley is drawn on your question sheet, I would always draw it on your answer sheet because you want to add forces to it and you want the examiner to see these. So the first thing I'm going to do is I'm going to sketch the diagram onto my answer sheet. I'm going to write A by the side and B by the side because I want to add things onto my diagram. Now the question telling me A has a mass of 2 kilograms, I'm going to write that there, and B has a mass of 5 kilograms. We're told there's a light inextensible string. The word light always tells you that there is equal tension either side of the string. So the tension is constant throughout. In other words, the tension here is the same as the tension here. The word inextensible means that the string's not extending in any way, which means the acceleration is constant. In other words, the acceleration of this object is the same as the acceleration of this object. So we're told it's passing over a fixed smooth pulley, so the pulley is not moving and it's smooth, so there's no friction. B is held at rest with the string taut, it's then released. So B is then going to move downwards because it's heavier, so acceleration will be downwards for B. Because B is moving downwards and because you've got an inextensible string, A is going to move upwards with the same acceleration. Now we need to add the forces onto the diagram as well. Now the tension in the string acts upwards for both objects towards the pulley, and this object has a downward force of 2g, that's its mass of 2 times gravity, and this one has a downward force of 5g, that is its mass of 5 times by gravity. So we've now drawn our diagram onto our answer sheet and we've added on the extra forces. So the part A is asking us to calculate the magnitude of acceleration, that means the size of acceleration, and the tension in the string. So what we need to do is we need to apply Newton's second law to both objects A and B. So applying Newton's second law to A, that's applying force equals mass times acceleration. In other words, the resultant force will be the same as the mass times acceleration. And we're also going to apply Newton's second law to particle B, which is also F equals ma applied to B. So looking at A first, force means the resultant force in the direction we're going. So because A is going to move upwards towards the pulley, then the force is going to be the upward force minus the downward force. So it's going to be T minus 2g, and that's going to equal mass times acceleration. So its mass is 2, and the acceleration we don't know is A. Newton's second law to B is the same, except that B is travelling downwards, so force is going to be the downward force minus the upward force because we're moving downwards. So the downward force is 5g, and we subtract t, the upward force, and that equals mass 5 times acceleration A. By forming those two equations, we've actually got a lot of the marks already, so now we need to simplify them and solve them. So remember, g is 9.8, so we can now say for A that t minus 2 times 9.8 equals 2a, and 2 times 9.8 is 19.6, so this simplifies to t minus 19.6 equals 2a. This equation over here, we got g is 9.8 also, so 5 times 9.8 minus t equals 5a, and 5 times 9.8 is 49, minus t equals 5a. So now that we have the equations as simply as we can, we now solve them simultaneously. So we're going to write them down over each other. So this one is t minus 19.6 equals 2a. This one I'm going to rearrange to write the t first, but it's a minus t. So minus t, positive 49, so plus 49 equals 5a. I can see now I've got a t in both equations, so to eliminate their different signs, so I add them. So t plus minus t is 0. Minus 19.6 plus 49 is 29.4, and 2a plus 5a is 7a. So to solve to find a, I now divide 29.4 by 7, and that will give me a, and now I can say that a is 4.2 meters per second squared. To find t, the tension, I now take either of my equations at this stage here. I'm going to take this one because t is positive. So t minus 19.6 equals 2a. I'm going to substitute in a as 4.2. So t minus 19.6 equals 2 lots of 4.2. So t minus 19.6 equals 8.4. So t equals 8.4 plus 19.6. So t equals 28, and the units are newtons. Now the last part of the question is asking me to explain what the assumption the word light means in the description. Well, light, as we said before, meant that tension was equal on both sides of the string. So we can simply say that light means equal tension throughout. Okay. Now, before we come on to answer question 8, which is where we involve calculus and mechanics, let's do a bit of background information. So, to get from displacement to velocity, remember on a displacement time graph, the velocity is the gradient. So to get from a displacement to velocity, we need to differentiate. And if we have a velocity time graph, then the gradient is acceleration. So to get from velocity to acceleration, we also differentiate. To work backwards, we do the opposite of differentiation, which is integration. So to get from acceleration to velocity, we integrate. If we know the equation for acceleration in terms of time, we integrate to get velocity in terms of time. And the same for going from velocity to displacement, we integrate that equation also. Now coming to actually do question 8. So a particle P of mass 3 kilograms moves along the horizontal x-axis under the action of a resultant force F. Its velocity v at time t seconds is given by v equals 12t minus 3t squared. Given that the particle is at the origin when t is 0, in other words, its displacement is 0, when t is 1, not 0, when time is 1 second, find the expression for the displacement of the particle from the origin at time t seconds. Our displacement is integrating velocity. So we need to integrate velocity in terms of t, which means we are integrating the velocity equation, 12t minus 3t squared, in terms of t. So integrating 12t gives us 12t squared over 2. Integrating minus 3t squared is minus 3t cubed over 3 plus the constant of integration. So 12 divided by 2 is 6 and 3 divided by 3 is 1. So displacement therefore is 6t squared minus t cubed plus c. So now we apply these conditions that we are displaced 0 at time equals 1 second. So 0 equals 6 times 1 squared minus 1 cubed plus c. So 0 equals 6 minus 1 plus c. So 0 equals 5 plus c. Therefore c equals minus 5. So our displacement equation is, when we substitute in our known value of c now, is r equals 6t squared minus t cubed minus 5. Now the last part of question 8, part B, is to find an expression for the acceleration of the particle at time t seconds. Well, we know that velocity equals 12t minus 3t squared. To get from the velocity equation to the acceleration equation, we differentiate velocity. So differentiating 12t, we get 12. Differentiating minus 3t squared, we get minus 6t. And that's our expression for the acceleration. Okay, question 9. A truck of mass 180 kilograms runs on smooth horizontal rails. Hopefully already you realise you need to draw a diagram for this one. So let's draw, horizontal means horizontal, like an x-axis. So you've got a truck that's on a smooth horizontal rails. A light inextensible rope is attached to the front of the truck. The rope runs parallel to the rails until it passes over a smooth light pulley. So horizontal to the rails until it passes over a smooth light pulley. The rest of the rope hangs down a vertical, so it's going to hang vertical down a shaft. When the truck is required to move, a load is attached of m kilograms to the end of the rope, and then the brakes are released. So the load is going to go downwards, acceleration is downwards, and the truck is going to accelerate to the right. Now we're told the truck was mass 180 kilograms. Remember, mass times gravity always acts vertically downwards, so 180 g is coming down here. Now, just as an object in a lift has a reaction of the floor onto the object, the normal reaction force, the horizontal rails are putting a force onto the truck upwards, which we call R. As always, we've got tension in the string, always acting towards the pulley, or rope in this case. So there's our force diagram. Part A is now telling us that the acceleration is 0.8. So we can actually change this A to 0.8 on our diagrams because we know the actual size of the acceleration. Now, we want to find the tension in the rope and the value of m, so the weight of this load here. So we need to apply Newton's second law to the truck, and we want to apply Newton's second law to the load. So Newton's second law is F equals ma, force equals mass times acceleration. Now let's make a note of direction. The truck is moving to the right. So when we're talking about the force, we mean the force to the right minus the force to the left. So the force to the right is the tension in the rope, but there is no force to the left, so it's minus 0. So don't be confused with R and 180 g. Because we're moving to the right, the force is the right force minus the left force, so it's t minus 0. That equals the mass of the truck, 180, times by the acceleration, which we know is 0.8, So in other words, T equals 180 times 0.8. Therefore, T equals 144 newtons. So applying Newton's second law, so F equals ma to the load. Now the load is moving downwards. So the force is going to be the downward force minus the upward force. Well, actually, we've forgotten to put the downward force on here. Remember, the downward force is always the mass of the object times gravity. So the downward force is going to be mg minus the upward force minus t. That equals mass m times acceleration, which we know is 0.8. Well, we know tension is 144. We also know gravity is 9.8. So we can change this to 9.8 m minus 144, because we know tension is 144. And that equals 0.8 m. So rearrange to solve for m. We've got 9.8 m take away 0.8 m equals positive 144. Therefore 9m equals 144. So m is 144 divided by 9. So m is 16 kilograms. Part B is talking about the assumptions. So in addition to the assumptions given in the question, so that's about the light inextensible rope and the smooth pulley and the smooth horizontal rails. Write down one further assumption you've made in your solution to this problem and explain how this assumption affects both your answers. Well, the main assumption we're always making with problems like this is that there are no external forces resisting motion. And the main one we are ignoring air resistance. Okay, that's the assumption we're making. How would it affect our answers? Well, how would it affect tension? Well, if we had a force acting this way, so remember our truck here had tension in the string this way. If we had a force this way, then tension would have to increase. Because the truck is required to move with acceleration 0.8. So T would be greater if there was a resisting force. Okay, now how would it affect our second answer, M? Well, the Newton's second law equation would alter, wouldn't it? Because our tension was carried through as 144. Now, if tension was greater, then the mass would be greater also, because we're dividing 144 by 9. So M would be greater as a result of greater tension. And finally, question 10. We've got two forces acting on an object. F is I minus 8j. In other words, the force is 1 unit in the x direction followed by minus 8, so negative 8 in the y direction. Force G is 3I plus 11j. In other words, 3 units in the x direction followed by 11 units in the y direction. Because we have two forces acting on an object, what we need to do is find the resultant force. So the overall force that these two amount to. So we need to do F plus G. So F is I minus 8j, and we're adding that to G, which is 3I plus 11j. So adding up the I components, we've got 1I plus 3I, which gives us 4I, and we've got minus 8j plus 11j, which gives us positive 3j. So that is the resultant force. Now, we are asked to find the magnitude and direction of the acceleration if the mass of the object is 3 kilograms. So finding the magnitude and direction of the acceleration, not of the force. So the first thing that we need is the magnitude of the force. So the magnitude of the force, which is the size of the force, is the square root of 4 squared plus 3 squared. This is because 4i plus 3j means 4 in the x direction followed by 3 in the y direction. So that is the resultant force there. So if we're finding the size of that, we're basically finding the length of the hypotenuse if we have a right angled triangle. So the square root of 4 squared plus 3 squared is 16 plus 9 square rooted, which is the square root of 25, which is 5. So 5 newtons is the magnitude of the force. Now to get the magnitude of the acceleration, we need to use Newton's second law. Force equals mass times acceleration. The force we've just worked out is a magnitude of 5. We know the mass from the question is 3. So 5 equals 3a. Therefore, A is 5 over 3 meters per second squared. Now, we also need the direction of acceleration. Well, the direction of the acceleration is exactly the same as the direction of the force. So we're going to put direction of force stroke acceleration because it is the same direction. Now, remember our resultant force was 4I plus 3j, and if I sketch that, that was 4 in the x direction and 3 in the y direction, the vertical direction. So the direction we're finding is the angle between that force and the horizontal. So it's a right angle triangle. We have opposite and adjacent. So tan of that angle of direction is opposite 3 over the adjacent 4. Therefore, that angle is the inverse tan of 3 over 4. Therefore, that angle is 36.87 degrees to the horizontal. Now that is the direction of the force and the acceleration because their direction are one and the same. And that's the end of our paper.